Hello! How you doing? I'm still getting over the jet lag and disruption that was my trip to Hackaday Europe. Let me tell you, it was worth it. I love Berlin. But I'm back in the lab, and today I want to try and create, simulate, and run a digital design on an FPGA and get it ready for inclusion on an actual ASIC. I'm Pat Deegan, currently going through an ASIC design course and sharing cool things I find along the way. Last time in this series, we saw how to get from top-level modules all the way down to transistors. Today, the focus is going to step back and go over how I like to get those hardware description modules ready, all using a very sweet toolkit. If, like me, you're extreme, or if you're interested in at least one of music or simple sound processing anyway, FPGAs, custom integrated circuits, or using Python to put all those things together, then come along as I try to make something cool. The goal for today is Project Neptune, a digital hardware guitar tuner, and the challenges are to get standard tuning, basically working for a 6-string guitar, do it so it's usable. We want to know when we're getting close, not just when we're spot on the target frequency. Do it in a way that's flexible, so we aren't married to this set of frequencies or use case. Do it efficiently, so it's small enough we can get it produced on an ASIC without breaking the bank. Do it all using open and Libre tools so you can play right now without any licensing hassles. And finally, to keep the whole thing simple enough that we can hopefully get it all done today. That may be asking for a lot, but with the help of Amaranth and Python, I'm thinking it's doable. We'll see. We'll start by going over what exactly we're doing and the high-level architecture, aka how I'm going to chunk the project down into manageable bits. Then the idea is to build each block, introducing Amaranth along the way, and do basic sanity checks with simulation. With all the modules in hand, we put it all together and try it out on a real FPGA, this board here. And if that all works, we can see if I can squeeze the whole design into the 150 by 170 micrometers afforded by a TinyTapeout slot and get it produced on an actual IC. Okay, let's get comfortable and started. So we basically need a frequency counter and a way to tell if we're on or near any from a set of frequencies of interest. At first glance, the standard tuning frequencies for a guitar can look pretty random, and though the particular starting point, say A2 at 110 Hz, might be arbitrary, once you've settled on it, then everything else is pure and delightful math and simple ratios. Now, I won't go into that theory here. If you're curious about the Western music system, do check out Donald Duck in Mathmagic Land. I'm serious, that may be the best thing Disney has ever made. Short version is that the heptatonic scale reflects mathematics of the universe that are leveraged by our ears. Simplest example of that is that an octave is a straight up doubling of frequencies. That's it. And you get that by vibrating a string that's half as long. Magic. But the upshot is that it's all nonlinear. A difference of 10 Hz means more at the low end than it does higher up. Around E2, the fat string, 10 Hz down is a D, and that difference is doubled an octave up, and 2 octaves up, that's 40 Hz to get from E to D. Since the strings on a guitar span 2 octaves of frequencies, this starts to matter. Now, because I'm trying to squeeze this into TinyTapeout, I want the same simple circuit to determine proximity, regardless of the string I'm tuning. So I'm not going to trouble myself with the nonlinearities at this stage, and it's going to be a compromise. Looser on the low end or really strict on the high strings. Try to find a compromise that works, we'll see. So let's get started designing. Okay, the first thing to consider is what's implied by but not included in the design. We're going to be processing some arbitrary analog signal here, and if it's coming from a guitar, it's going to be pretty small. So the first thing that's going to be outside the design but required is some sort of amplification. So let's say we're playing some guitar string. The signal that comes out is going to be periodic, but it's not going to be anything like a smooth sine wave. So the frequency is equal to 1 over the period, and the period is whatever's between the peaks here. But all this extra stuff is what gives the sound its timbre. It's how we can tell the difference between a guitar and a trumpet. So one of the first things we're going to have to do is pass it through some sort of low-pass filter. Now, if we do this with just passives, these are low frequencies, so the inductors are going to be massive. I don't know, 30 millihenries or something like that, 60 or 90 ohms of internal resistance. Not too pretty. So maybe this thing will be a silent key, some sort of active filter anyways. So we get a little bit of gain and we get filtering and it comes out. So what comes out of here is then something a little bit more smooth, not a sine wave, but better. From there, it's a question of determining what is above and what is below the threshold here. So next we're going to feed that in some sort of threshold comparator thingamajig, and what's going to come out is finally a digitized signal. This signal will go high when we're above the threshold and low when we're below. So whatever H and L is defined, probably 3.3 volts. And now we have digital. Hooray. So this train of pulses is what's going to be fed into our circuit. I'll actually implement this later. If you're curious about it, let me know, and I'll do a video or something. So now we can get into our actual design. So we're getting some train of pulses coming into our system here. The logic levels are valid, but they're pretty much arbitrary widths. So the first thing we're going to do is feed this into an edge detector. Now this thing has two jobs. All the little red blocks I'm going to draw here are synchronous logic. So there's a lot of flip-flops and stuff involved, and they're all clocked and they're all going at the same beat. The input pulse, however, doesn't care about any of that. So it's basically going to need to cross the clock domain. Why that's important is that basically the flip-flops, if you don't respect setup and hold times, you can get metastability, and that can cascade through the whole system and just cause a giant mess. So the edge detector here is going to output a stream of pulses that tell us when the rising edge was found here. This guy here, this guy here, this guy here. And most importantly, we're going to synchronize all this with the internal clock. So these guys will be safe to consume, and they'll be exactly one clock pulse each. So that'll make our next bit simpler. That next bit is going to be a pulse counter. So it gets two inputs here. The first is the train of pulses that has been sanitized by the edge detector. And the second is the measurement period. So the measurement period is a configuration, and it's going to come into the pulse counter and say, count the pulses for this many clock cycles, and then tell us the result. This could be 1 second, in which case the number of pulses would be the frequency in hertz, but that would make for a slow tuner and is kind of inflexible. So I'm basically going to tell the pulse counter, okay, measure it for this many clocks, and in that case, just give me the result, and we'll just calibrate everything based on that. So what comes out of this guy is now the count over the period in question. And this gets fed into the most interesting block in our little set that I'm calling the discriminator. Now the discriminator's job is to take the number of counts that just came in and decide whether this is one of the frequencies of interest. It needs to report two things. A, is it a frequency that we care about? And B, how close are we exactly? Are we getting there? Are we spot on? What's the situation? So what comes out is the labeled frequency, labeled target, let's call it, or none found, and the proximity. So are we far away? Are we close? What's going on here? Now to output that, it needs more than just the count for the given period. It needs to know which frequencies we care about. It has to have some sort of mapping of count to label. So two things come in, the actual count measured and the mapping. I mean, it's not really external, but I'm going to separate it out just to make things clean and make the code usable for other things than just guitars. So the discriminator could be some sort of system where we're basically comparing the count to all the values at the same time, because this is hardware. If we have enough space, we can just do everything at the same time and get the one result in no time at all. But the trade-off is space, and TinyTapeout, not so much space. So we may end up instead having some sort of FSM implementation. So I'm going to have a look if I'm going to try and figure out how big this would end up being, these gates here, how much space that would end up taking. Take a guesstimate. If that doesn't work out, I'll move to the FSM and just do it step by step as a sequence. So once we have our target labeled, this is string A, this is string B, this is string nothing found, and the proximity, we're very close, we're spot on, we're far away, something like that. This gets fed into our final block. The final block is going to be some way of showing us what's going on. With TinyTapeout, we only have 8 inputs and 8 outputs. So that's what I'm going to limit myself to. It's not much, but it's plenty because of this. This is a dual 7-segment display, and the neat thing is you can drive 7 segments with 7 pins, and the cathode is basically switched one to the other. So you're basically displaying both at the same time as you're illuminating one and then swapping, illuminating the other, back and forth. And we're going to have some sort of letter representation of the chord and, you know, something to indicate proximity. So I'm going to call this the display driver. And what it takes in is the label output by the discriminator and the proximity. And for config, we're going to have a mapping of label and prox to segments. That's pretty. So it takes these two things in and then just sends out the output to the 7-segment display driver. And that's it. We're done. So these are the main blocks. There is a surrounding block that's basically the glue that wires everything together that we're going to have to make. And actually, I may end up doing 2 because I want to output it onto the FPGA first, and then after that, get it ready for TinyTapeout. See how that goes. Now, we could do them in order, just follow the input all the way to the output, but the most interesting bit is the discriminator here. That's where all the work happens. Basically, we're going to construct the map and then see how exactly to implement that. So I think I'm going to start with that and then go over all the other bits and just glue it all together, see how it goes. So let's code up a design. Oh, wait a second. While we're here, let's think about the discriminator a bit because it's kind of complicated and it would be fun to get it right. Now, its job is to label frequencies. So let's keep it simple and just think about one, frequency X. Now, frequency X is somewhere on the spectrum here, right there, actually. Yeah. Now, as mentioned, I want to be able to know whether we're close or not. So let's define some span here that is going to be where frequencies of interests lie. You're getting close to X if you're within this range here. So let's say the span is some number, we'll call it 32 hertz. Then any pulse count between X minus half of 32 and X plus of 32 is going to be within this span, and we're going to call it close. We're going to label it X and say you are close. Now the question is how close? Now an easy, inexpensive way of doing this is to do a subtraction. So what we don't want is negative numbers ideally, so we're going to start with the max frequency here, so MXF say, and this is equal to X plus 1/2 of the span. So when a pulse count comes in, all we have to do is take max frequency, subtract pulse count, and we're going to get some value. Assume we're in the green here. That value is either going to be smaller than 16, it's going to be 16, or it's going to be greater than 16. Now 16 is just my midway point here. If it's 16, we're exactly on the frequency. All right, you have tuned your string. If it's below 16, it means that X number was higher than half here, so it's above. So this is above, and the closer it gets to 16, the further down this way we come and the closer we're getting. Now, on the other side, if it's bigger than 16, then it means that the X value was somewhere over here, so it's below. And in this case, the logic is inverted. That means lots of circuits. One way we could fix this is to take this special case here when we're greater than 16, come over here and do span minus, diff, minus diff. In that case, what we're doing is flipping things around. So say it was exactly 16. Well, then span 32 minus 16 would be 16, which means, exact, we're right on it, right? And the bigger it is, if it's 32, then we go down to 0. That means that the logic for this guy above and this guy below becomes the same. 0 is far, and then 16 is exact. That's pretty cool. So now that we have the basic logic, all we have to do is, implement it.